everyone. Welcome to IEEE Tech Insider webinar, and I thank you all for joining today. I'm Jae-ha Kim with Scientific Analog, and I'll be moderating this webinar today. Today's webinar will address how to write UVM SystemVerilog test benches for analog mixed signal circuits. The speaker I present is Charles Danchak. He currently teaches SystemVerilog at UCSD Extension, and also consults on various hardware description language-based design and verification projects. This talk is about 90 minutes long, and we have a few breakpoints in the middle for Q&As. So if you have any questions, please type them in the Q&A window. There's a separate window for a Q&A other than this chat board. And so type your question there anytime. And during one of the break session, I will select a few and ask Charles on your behalf. So now, without further ado, let's welcome Charles.
Thanks, Jae-ha, and welcome everybody. Glancing through the roster, I saw a few familiar names. So if you've been a student in one of my SystemVerilog or maybe DFT classes, send me a chat and say hello. Anyway, welcome. So we've got about 60 slides to cover, so I'm going to go pretty briskly. We're going to talk about a few UVM features, hopefully not the usual rehash, but I'm a hardware guy, and I'd like to cover UVM, as abstract it is, on a more intuitive basis. So we'll look at several axioms of UVM. Then we'll look at how in the world we can take an abstract class-based UVM test bench and hook it up to an analog bandpass filter. One of the keys, of course, is to hook things up using interface buses. We'll look briefly at that. We'll run a simple test, and we'll see how the driver object applies stimuli and the monitor measures response. Keep in mind that we're talking about analog response in this case. We'll look at a scoreboard in a real working example in detail. We'll run a simple test suite with one sequence, and we'll work our way up. We'll extend that to several sequences and get a pretty robust test of our programmable filter. And in section 9, we'll talk about, gee, with such a wide passband, with all these modes, have we really covered all the functionality of this analog design? And we'll finally see if we hit 100%. So that's where we're going. In this section 1, let's take a look at the block diagram of our test bench. And then we're going to cover 4 principles. I like to call them axioms of UVM. We could easily have a dozen, but for time limitation, let's just look at these 4, which are most pertinent to our talk. So here's our block diagram on slide 4. At the very bottom of the hierarchy is the bandpass filter DUT with its digital control logic. It's instantiated inside of a fixture submodule, which also includes the instrumentation we need to apply sinusoidal input and measure the sinusoidal output. And the square-edged rectangles denote modules in this diagram, whereas the round edge denote objects in the class hierarchy. This is shown in dashed outline because it's actually instantiated within the top-level test bench, and we'll see that later in section 7. Anyway, using interface buses, physical port to virtual pointer to connect that with the class hierarchy. So the driver's job is to take the latest data packet with an applied frequency and mode and drive those signals into the fixture. On the monitor side, it's looking at the monitor side interface bus, grabbing the measured peak-to-peak amplitudes, assembling those into a packet, and then via TLM ports and TLM paths, we send those packets on up to the scoreboard where we can do a comparison between the actual measured gain, amplitude out over amplitude in, compared with the expected gain, which we get from a SPICE-generated reference model, basically a set of 8 lookup tables, one for each mode. We'll see that in detail in section 6. Finally, at the very top level, this is the top level object in our class hierarchy. Many people refer to it as the test, but in keeping with Cliff Cummings' nomenclature, I prefer to call it a test suite, because you can only run one test suite at once in a UVM simulation. And wow, the good news is that you can actually select it at runtime without recompiling any code. So there's our block diagram. Let's look at the first axiom. All the components in UVM derive from a base class. This package gives you access to the base classes, a huge volume of code, and we do a wildcard import to bring them in to any source code file where they're needed. And we use the SystemVerilog keyword extends so that we can derive our own customized class from one of the base classes, such as UVM agent. So that's the basic idea. Let's look at 2 use cases. Simplest one, we may use a base class as is without any customization. And here we're using the sequencer base class. We don't need anything fancy. We're not, in this simple example, we're not looking at round robin or any other kind of arbitration between sequences. So we can just instantiate it as a plain sequence SQR. Remember from your OOP courses that an object is an instance of a class. The only different thing we're doing here is we're specializing this sequencer class to the type of packet we're using. So we can send a stream of packets, from the, my mouse is a little wild sometimes, so we can send those packets, a stream of packets, down to the driver. Second use case, excuse me, we can write a customized driver class. Ours is about 80 lines of code. We're just showing the first line here, but notice it extends UVM driver base class. And so we're instantiating that inside of our agent. Here's the object. And notice one of the key things it inherits from UVM driver is this handy transactional level modeling port called sequence item port. We'll make heavy use of that later. So all the components in our hierarchy come from a base class. That's also true of transitory objects that are not necessarily a fixed part of the class hierarchy. So here's our first look at a sequence which sends a stream of data packets with the filter in normal operating mode. And most of the action is inside of this body task. And it's an untimed algorithm that generates a series of packets. And we'll use knobs from the command line, in this case 3, that sends 3 packets from sequencer to driver. And we can update non-random fields. For example, every packet has an integer tag. We can increment that. In particular, though, we're going to randomize the frequency that we want to apply to our filter and the mode we want to put it in. And so that's all done inside the sequence. So notice it's derived from this base class and has all these handy features. All right, so all of the packets shuttle around the class hierarchy along these TLM pathways. Let's take a look at just one pathway. This is one of the most challenging parts of writing a UVM test bench, in my humble opinion. So let's walk through it. So these TLM pathways are abstractions of an OOP mailbox. but the user never actually sees the mailbox. So our first job is to build any ports that are necessary. This diamond shape icon is neither a regular port nor an export. It's an analysis port, meaning that it can go to more than one subscriber. We have two. And so we construct that port during build phase. We also need a corresponding port on the agent. And when they're in place, we can then, during connect phase, invoke the connect method, and this thin red arrow symbolizes the connection path, the TLM pathway. We'll talk about phases in our fourth axiom, by the way. Then we continue. We connect more TLM ports together. This is an export, a little round circle, and we've hooked that up. And finally, because this coverage object is derived from the subscriber-based class, it has a built-in export with this fixed name. So we can connect it to APD1, and analysis port, driver side, level 1 in the hierarchy, and we're done. So we're now in position to send stimulus packets from the driver on up to the scoreboard. What kicks off the sending is this call to write. So there is a typical TLM1 pathway. Next axiom, UVM configures a test bench using a decentralized database facility named UVM ConfigDB. We're going to use this in a very important context when we connect our physical interface buses to their virtual destinations. But it's not easy to understand what happens. So let's start with this very simple example. Let's pretend we've got a hypothetical knob or parameter called minimum coverage. Maybe it's 99%, or maybe we're just early in the flow shooting for 65% coverage. Is there a way to write this value into this decentralized database where any object can get a hold of its value? Well, this is what you do. We run the set method. The database is never actually instantiated. So both the set method and the corresponding get method are static. So this scope resolution operator allows us to directly call the set or get method of this class at any point in the code. And so we can now allow this instance, the coverage object, which is lives in the environment, which is under the top level test suite. There's no class object involved here because min coverage is defined in a test bench module at the very top. And so we set the class pointer to null. And then the end result is that we've stored a key value pair, sometimes called a resource, in this decentralized database where the coverage object can grab its value. So later we'll see how we can apply that to interface buses. Last axiom, a UVM simulation is phased. There is actually a class object called UVM Phase, and we start at time 0 before any time advancement to build all the components in the hierarchy. We've seen examples of that already, and connect things together like the TLM ports. We also call set and get during build phase. Then, when we're ready to advance simulation time, the run phase kicks in. This is the only phase that time advances. And every run phase task, we'll see a few examples one in the driver, one in the monitor, one in the scoreboard. Each one is given a thread to run by the UVM machinery. And by the time it's all done, we are then done advancing time. There are a few other optional phases where we can extract data across the entire run. For example, what is the worst case discrepancy that our scoreboard detected between the actual values and the expected, and we can report all the results. So all of this machinery is built into the UVM base classes. So I like to think of a UVM test bench as a very intricate but highly configurable machine. All we have to do is write the necessary source code, like our customized driver and monitor and so on, and print out the test results. Everything else happens almost automatically. The phasing, the configuration database, the untimed sequencing, and so there's a huge amount of functionality here. But the good news, you only need to tap into the functionality you actually need to test your analog mixed signal DUT. All right, let's go on to section 2. Let's drill down into our DUT and we'll try to answer the question, how in the world are we going to connect this very abstract UVM test bench with TLM ports into a piece of hardware, a bandpass filter, or a LDO voltage regulator, or a TRX transceiver? Well, let's start by looking at our DUT. This was designed in Virtuoso. At the heart is a two-stage CMOS op-amp, and the feedback network has various resistors and capacitors that we can switch in and out using these CMOS transmission gates. They're controlled by these 4 digital logic cones. In turn, they're controlled by 4 input bits. These other inputs, by the way, are VDD and VBN, which during power down bypass mode will get cut off from the op-amp. And so the only thing that looks different about this Virtuoso editor to any Virtuoso expert out there is this sidebar. This is XMODEL's Glister toolbar. We can run various XMODEL capabilities here, like launching a simulation, looking at the analog waveforms in a viewer, or as we'll see on the next slide, we're going to extract accurate transistor models and RNC models. So let's drill down into the two-stage op-amp on the next slide. Here it is, 9 transistors. We'll assume that it's built for a default 45 nanometer CMOS technology. There's the process design kit. And a common question we get right off the bat is, well, does your model, are you just using canned transistor models? Well, the answer is no. We're going to run a utility we call ModelZen that does the following. Let's use this transistor, this tail in the diff amp, to illustrate it. We extract the net list, and here's the N-MOSFET model for this particular this transistor. This is one of the XMODEL primitives, one of many. And the only thing that remains as the designer entered them is the width and length. For example, we're still at 12 micron width. Everything else, from threshold voltage to output resistance to process transconductance, will get models and will fit it by silently running SPICE or Spectre in the background. So we have very accurate sign-off quality parameters here. We're actually looking at a simplified version. Many of them are not just a single number, but arrays of piecewise linear values. So we get sign-off quality ready to simulate SystemVerilog source code for the entire bandpass filter. So that's our DUT. Now let's zoom out in Virtuoso. Here's our DUT inside of the fixture submodule. And we're going to see how the instrumentation allows us to apply a sinusoid to the filter input and measure the amplitude of the sinusoid coming out. So let's focus on the stimulus chain. You can drop these primitives into the Virtuoso schematic or instantiate them in the code as you prefer. This sine function applies a sinusoidal input of specified frequency and phase and amplitude into the filter. And so we selected out of the XMODEL primitive library. And on the next slide, 15, let's look in detail what happens. Let's suppose that in this running example, our current transaction wants to apply a randomly chosen 34 kilohertz frequency sinusoid to the DUT at 100 millivolt amplitude. So we need to first convert that ordinary real value, 34,000, into XReal type, which is XMODEL's workhorse type. It's actually a struct, and it contains not only the real value, but also other information that allows XMODEL to simulate analog signals with near logic simulation speeds. Now, how do you convert a constant into an actual sinusoid? Well, you integrate it over time. So ft ramps up, and if we do that modulo 1, the ramp drops back down to 0, and we start all over again, and we got a nice periodic sawtooth waveform. If we scale that by 2 pi, we're talking about omega t as opposed to ft. We can feed that as the argument into our sine function, and that generates the sinusoidal input at the desired random frequency and amplitude. And we get a sinusoid of the same frequency coming out at some lower amplitude. And so as a guideline, we recommend encapsulating all the analog functions, instrumentation, and signals of XReal type or its digital counterpart, X-bit type, inside this fixture submodule, which we can, as we'll see later, instantiate inside the topmost test bench. In case you're wondering, there are handy data sheets on all these primitives at the Scientific Analog website. And they're similar to Unix man pages. They're very concise and easy to read. So for example, here's our sine function with its XReal input and output and its real amplitude, which you can enter as a parameter. We call ours Vin. And here's the output of the function that we feed into the filter. Over 100 of these primitives in the library. Let's turn our focus to the response chain that measures what's going into and out of the DUT. So we have 2 primitives, both called measure peak to peak. And to measure a peak to peak amplitude, you need to do it over at least 1 cycle time interval. So we have 2 trigger signals, we call them tick and talk. They're generated by ordinary procedural Verilog, SystemVerilog code from the packet clock. So on slide 18, here we bring in the clock along the interface bus. We assume we're launching new stimuli at the very beginning of the cycle. So there's half a cycle of settling time. And then this yellow highlighted interval between tick and talk is where we do the peak-to-peak amplitude measurement. These have to be converted from ordinary bit type to X-bit, which, again, it's a struct. It contains the logic value 0, 1, X, or Z, as well as other information that allows accurate simulation of almost analog edge placement and pulse width. So we feed those to both measurement primitives, and we then they both output real values that are ready to use. And so here our actual gain is 160 millivolts over 200 or 0.8. What about the digital control bits? No primitives needed there. We can feed those directly into the control logic inputs of the DUT. And so for normal filtering operation, we want the bypass power down bit deasserted, and the other 3 bits fiddling with the resistors and capacitors in the feedback network select a given passband mode. In this case, it's mode 7. And so we're ready to test the filter. We've chosen the mode and the input frequency, and we're ready to test it. Just a guideline, we found by practice that it's best not to apply these bits individually. We enumerated them as a SystemVerilog enumerated type, and we can then refer to it by name. So here's our design spec. If that most significant bit is high, the whole entire DUT is in power down bypass mode. If it's low, we can select one of 8 passband modes and refer to them by name. Here is the enumeration type definition. So we can, in our high level UVM code, we can now refer to these names instead of their encodings. And this mode type is defined in the data package. We can import it wherever we need it. Just to make the names more human readable and to demonstrate how seamlessly compatible XMODEL software is with SystemVerilog syntax, we're using escape names that enables us to use the dash in the middle. And so we've got a trailing backslash, trailing white space and leading backslash, and we'll refer to those names throughout the code. Okay, let's go to section 3. Let's see how we can hook the fixture up to the class hierarchy. We'll need 2 interface buses, one for the driver side, one for the monitor side. So as my old students know well, I'm a hardware guy. I like hardware analogies. So I look at an interface bus as a gray cable containing a bundle of related signals, which we'll see their definition on the next slide inside the interface code. We can also splice external signals, which are defined higher up in the hierarchy, like the packet clock and the reset. And so they're all mingled into this interface bus. And inside the fixture, we can refer to any individual signal simply by using dot notation. So we can say dot packet clock or dot mode or dot PPAN. Notice you're prefacing the dot by not the instance name of the interface bus, but the port where it comes in to the fixture. So we have access to all these bundled signals. Here's the interface definition. Notice we're reusing the same interface bus both on the driver side and monitor side. Each will emphasize a different subset of the signals. And we're importing data package where we define the mode type, and then we have access to all these signals. Just defining an interface bus doesn't do the user much good until you actually instantiate it. So here inside the topmost test bench module, where we describe the clock and reset and instantiate the fixture, we're also instantiating both interface buses, diff and mif, and splicing in the packet clock and reset we just defined. So that'll enable us to connect with the class hierarchy. But wait a minute, classes in SystemVerilog cannot have ports, I/O ports. So how in the world are we going to connect these hardware buses with a class? Well, the secret, as we mentioned earlier, is to use the decentralized database. We're going to store key value pairs that associate MIF, the hardware interface bus, as I think of it, and its virtual counterpart. So on this slide, we'll look at the set call, and on the next slide, we'll look at the get call. So we've already covered this. So I'll just show that we're putting a resource, a name value pair, into the database. We have to reproduce this string name exactly when we do the get on the next slide. But there it is inside the configuration database. Then going to slide 25, part 2, this is called during the build phase of the monitor. We invoke get, we have the same key, and this time we're making the association between the stored MIF and vMIF. So in plain hardware terms, we're in effect connecting the hardware MIF data bus instance to the virtual pointer vMIF that the monitor can use to access signals. It's as good as having the instance name itself. Okay, before we go on, let me mention that our XMODEL based flow is compatible, at least in principle, with the emerging UVM AMS standard. They published a great paper at the recent DVCon, which we attended. This picture is actually from their last year presentation, but you can see that what they call the harness is very similar to what we term the fixture. It has analog resources inside of it. We can use resources from the XMODEL library. So very similar in principle. The only real difference is that with XMODEL, there's no co-simulation needed. All right, to keep things interactive, as Jeha mentioned, we have a microsecond quiz. So see if you can answer these questions. And this is a good time to post any questions by clicking the Q&A icon. And Jeha and Raphael will be glad to answer, or myself. While you're doing that, I'll just walk through these 5 questions. So number 1, a class cannot have any I/O ports. Mm-hmm. Number 2, an interface bus to be much use at all has to be instantiated. Mm-hmm. And number 3, we access the decentralized ConfigDB using 2 static methods, set and get. And 4, we'll get into this in more detail in section 7, we have to call run test from the top level test bench to actually launch the test suite and make the simulation go. And 5, a UVM test bench usually stops. Usually we don't call $finish manually. Instead, the machinery waits till all objections have been dropped. Any questions at this point, Jeha?
Well, we don't have any questions posted yet, but I can start with a simple question. So you explained this UVM ConfigDB that can store some sort of parameter database. There's a pair of the key name key, and a value. Is it possible to store value of any type? Looks like you can store the virtual. Actually, yeah. So that's the first question. The second question is, what is a virtual type? Yeah.
It's a very good question. The word virtual is, in my humble opinion, highly overused in the SystemVerilog language. It means different things in different contexts. So in this case, when you're talking about the virtual interface, it's simply a pointer taken care of behind the scenes. The user really doesn't have to do anything except the set and get methods we saw. It's simply a class pointer to the actual physical interface bus instance name.
So it's a kind of a pointer that can point to any type of class, any type of object.
That is a different story. This is meant to work with interface buses. Gee, that's a very good question. But I'll take a conservative stance and just say this only works for interface buses. For a ordinary object, you'd have to maybe do more customization.
Okay. Okay, just maybe one more question. I mean, what is interface bus for? It looks like it bundles multiple signals together, but how is it different from using struct type, which can also do the same thing?
Very good question. If anybody out there took my SystemVerilog for synthesis class, you know that you can even synthesize in an interface bus. It's a way of managing a complex busing fabric. You have everything collected together, all these related signals, maybe even functions, checking bus protocols and so on. You've got it collected in this nice, handy, named bundle that you can instantiate wherever you want to on the chip. So although you could do the same thing with just plain traditional Verilog signals individually, in a complicated system on chip design, it can save you a lot of low-level errors and hair pulling by having this named bundle called an interface bus. And we carry over the same concept to UVM Testbenches. Our interface bus is certainly not synthesizable because we've got real signals thrown in there, but it's the same idea. It's a way to collect all the related signals together and still be able to access them individually.
Thanks, Charles. Just in case, if people haven't found out, there is a icon named Q&A. Oh, yeah, and you can post question there. There is a anonymous question. Where do you see this technology best used for? I guess the question is about what is UVM for?
Well, that's a good question. I know we've got a very wide set of backgrounds in the audience. So the reason UVM, Universal Verification Methodology, was developed in the first place was that companies were spending so much time and effort on the verification task for a large system on chip. Managers decided, gee, we've just got to have a method of creating more reusable code that we can use in the next generation of the chip, in the next test bench. So UVM is an answer to that question. I think I've mentioned at several points during the talk that many of these classes and objects are highly reusable, and only the driver and monitor have intimate knowledge of the details of the DUT, pinout, and timing. So it is highly reusable, and there's a lot of very sophisticated machinery like the phasing system that the user can just employ without even really knowing, how it all works in detail.
Okay, Charles, I think it's about time to move on. Yeah, we'll have another Q&A session towards the end.
All right, great questions. All right, so let's tie everything we've covered together and look at a basic filter test. So we're going to test our filter during normal operation, and we're going to, the driver will take its latest packet that it got from the sequencer, disassemble the packet fields, and here's our running example. We're assuming 34 kilohertz, generate a sinusoid, apply that to the filter inputs along the interface bus, and drive mode 7 into the control input bits. And so there's the first half of this transaction. We've applied the stimuli. Then the other half of the transaction, we want to measure the amplitude coming out and assemble these peak-to-peak amplitude measurements into a data packet and forward that on up to the scoreboard. So the response packet is the other half of this transaction, and we can then compute the actual gain as the ratio of amplitudes. And so there's our basic test that we want to do over and over again with different random frequencies and modes. So let's first look at the code for one of these packets. Now, based on one of the questions that was just asked, you may be wondering, why bother to create a packet class with all kinds of fields and all this OOP stuff? Why not just use a variable, maybe an array or an array of structures to model each transaction? Well, several reasons. Only in a class can you randomize specific fields at will by calling the built-in .randomize method. Here we've declared both the integer value of the frequency and the enumerated mode. We've declared them both as random variables, so they'll be randomized when we call this method. We can also, I should mention, this will be a uniform random distribution. So as is, we could get a frequency ranging from 0 to 2 gazillion. Well, we want to constrain that to the passband range of our filter, 10 to 120 kilohertz. So we can write a constraint, use the SystemVerilog inside operator to make sure that whatever random value for fint was picked, it's got to fall within this bracketed range, 10 to 120. So these are all advantages of a class-based packet. One more is that sometimes large simulations can run out of memory. I worked at Synopsys for 10 years, and believe me, it's a common problem. So with dynamic packets, once you're done using a particular packet, you could set its pointer to null, and it's gone. It'll no longer use up memory. Here's the other side of our packet. We've got, a detail I should mention. Since we're using VCS simulation in this webinar, we don't yet support randomizing a real value. So we had to randomize the integer frequency and then cast it to a real. And we can do that in the post-randomize method, which is automatically called once .randomize finishes. Anyway, here's the two fields of the packet we need on the monitor side. And so we'll send those on up to the scoreboard. All right, now here's more detailed code for our sequence, the basic filter test. We looked at this briefly, but here's a little bit more detail. The sequence contains a body task. It's a required name. And we first set any non-varying fields. Like here, we deassert the power down bypass bit to make sure the filter's in normal operation. Then we go into a loop. This is a real for loop as opposed to forever loops we'll be running into from here on. And we bring down trials as a knob from the command line. So we get a series of 3 packets. We start them and we finish them. And we increment any non-random fields like the integer ID tag we stick onto each packet. And we can also randomize the frequency and mode. So what do we get? We get a stream of untimed packets sent from the sequencer's export to the driver's port. And notice it is completely untimed. It's left up to the driver when to apply the various fields to the DUT. Here's a transcript from a run with 10 trials. And so notice we're getting random frequencies and modes. Thanks to Dave Rich, one of his many useful blogs, We learned how to ensure cyclic random behavior for the mode. I won't go into detail here for lack of time, but we're ensuring that the mode does not repeat until all 8 values have been used up. As Dave suggested, we used a queue to ensure that, and a constraint. And otherwise, they'll repeat quite frequently. So all this is untimed. We leave it up to the driver and monitor to supply the actual timing. So let's look at our timing budget for this project. So guess what? As fancy as UVM is, as sophisticated as the base classes are, it has no way of knowing what timing scheme you want to follow. So the one we picked was, first of all, we wait for the reset to deassert, showing some relevant code snippets. So whether you're in the driver or the monitor, you have access to the reset via the interface bus. So we wait for reset to deassert, and then the action starts. On every rising edge of the packet clock thereafter, that's when we drive the new stimulus, frequency and mode, into the DUT via the fixture. We allow a full half cycle of settling time for transients to settle out. And then we have a yellow highlighted time interval where we carry out the peak-to-peak amplitude measurement. We refer to this parameter as the dwell time. And at this point, on any transition of talk, the monitor can grab the real amplitude value as needed. So here's the code snippet in the monitor run phase command. Oh, small detail, many of our XMODEL primitives incur 1 time step delay. And so since we're using a rather coarse time step of microseconds in this example to keep things simple, we added a delay time of 5 microseconds to allow for those delays. Okay, as a guideline, and believe me, these were all, many of these guidelines came out of hard-learned lessons. Be sure you write a timing diagram and get it all settled before you start coding the driver and monitor. You'll save yourself a lot of effort, hard experience. Okay, let's go on to the driver and monitor details in section 5. All right, we'll look at the driver first. The all-important task is run phase, but before we can execute it, we need to do some setup. So let's look at the setup code first. On the next slide, we'll drill down into the task. So we need to declare a packet first. It's of packet type. On the driver side, we refer to it as TX packet. We also need, we're not only sending this from sequencer to driver, but also forwarding the same data on up to the scoreboard for evaluation. So we need this analysis port, APD0, analysis port driver side, and we can then in build phase construct it. And then this is where we call the centralized database, we call get to associate vdiff with diff. So that gives the run phase task direct access to any signals in the interface bus, such as reset. So let's drill down into the run phase code. Now we've got a forever loop, not a for loop, but a forever loop. The idea being we want the driver code to be highly reusable, independent of test length. And as our timing budget showed, we're going to start the action driving stimulus into the DUT on every rising edge of packet clock after the reset is over. And we're going to use these two important base class methods, get next item and item done. Notice they both include the word item. and more on that later. But here's where that method is defined. It's within this little object sequence item port, this little square icon, which our driver inherited from the base class UVM driver. So another example of the built-in functionality that we inherit from base classes. And so get next item will pull down the next packet from the sequencer, and then we can disassemble the packet and send values like the integer frequency over the interface to the DUT. Now I'm glossing over some details here which are worth going into on the next slide, and I'm going to draw on a very, very good paper by Stu Sutherland and Tom Fitzpatrick. We're going to look on the next slide at the sequencer driver handshake. And the user doesn't really have to understand all the details, but I think it helps motivate us when we have some idea of what these 4 methods are about. They all include the word item. So let's quickly run through it. So step 1, we have started the sequence filter on our sequencer. That executes the body task. It comes to this start item task. That waits for the driver. And so we're waiting for the driver to wake up and request the next packet. Step 2, in the driver loop, get next item is called, and then it waits for the packet pointer to be received. Now, if you were watching carefully, the last slide showed the argument to this method is tx packet. So that supplies the pointer to that packet, and now the sequence loop can continue. It'll randomize the packet fields, assign any non-random packet fields, and when it reaches finish item, that's when it actually sends the completed packet to the driver, and the continuation of the loop is temporarily blocked. And in step 4, the driver has applied the values in the packet pointed to, driven them onto the interface bus where the DUT gets them, and now item done is called. In the simplest case, it has no arguments, and it unblocks the sequence loop to continue. So short story, that's how the sequencer driver handshake works. This is all built in to the UVM machinery. All we have to do is call those 4 methods at the appropriate time. Okay, monitor code. Again, we're going to focus on the run phase task where all the action is, but here's what we need to do to set that up. We need to declare a packet. We call the monitor side packet RX packet. We need a port in order to forward the response data to the scoreboard, and we need to get the virtual pointer to the physical MIF bus. Slide 40, here is the run phase. After reset is over, the monitor waits till after mid-cycle. It's waiting for that yellow highlighted time interval to end, and then on any transition of talk, plus the little bit of sample delay, it creates a new packet and then proceeds to, from the peak-to-peak amplitudes coming in on the bus, assemble those into packets and write those on up to the scoreboard via the TLM path. So I hope you're seeing how all these functions play together, this very intricate yet highly configurable machine we call a UVM test bench. Let's briefly talk about an agent. This doesn't have much functionality in it. There's no run phase task, but it does. We do need to construct some of the pieces. We need a port at this level, APM1. And you may be wondering, what is all this about constructing some things and factory creating other things? Well, as the guideline indicates, ports can be constructed in the usual OOP manner simply by calling their new constructor function. And that's all we need to do with ports, TLM ports, because there's no need to substitute those for a variant at runtime. However, other things like monitors, drivers, and packets need to be factory created. It's not required, but it's highly recommended, because at runtime for a given test suite, you may need to swap in a different kind of monitor or a different kind of packet, maybe to inject an error. And we won't be using that much in this example, but on our next paper, we plan to demonstrate that factory substitution capability. So this is a factory create of the monitor object inside the agent. Then we go into connect phase. We call the connect method to draw a thin red arrow between these ports, and we're done. There's our monitor side agent taking care of that entire output side interface with the DUT. Okay, at last, we get to the scoreboard. This is probably the most DUT-specific part of the test bench. And for that reason, you don't see many working examples of scoreboards in the literature, even for digital test benches, let alone analog. But here we're going to present a complete working example. So we're going to use a spice-based reference model to look up the expected amplitude from the filter given the input frequency. And we've got a set of 8 lookup tables, each one generated by SPICE, each SPICE for a different mode. And we found it very useful to use a SystemVerilog associative array. So it's an array of real voltage values indexed by frequency, for example, 12 kilohertz. And so notice for an associative array, you declare it with the index data type, not just an actual integer. And so each table is about 100 real values indexed by frequency. And then we declare a variable of that lookup table type, associative array type, called goldref, which will stuff it down here with whatever this function select table returns. So let's watch the action as the next stimulus packet comes up from the driver, gets queued up in this FIFO. And so here's our latest packet, 34 kilohertz, mode 7. When select table sees that mode, it selects one of 8 tables, and the scoreboard run phase software scans the table, finds the closest match to 34, and so we get an output of 80 millivolts divided by the input amplitude of 100. That gives us an expected gain of 0.8. Meanwhile, on the monitor side, we have the monitor side packet coming up through this FIFO. Peak-to-peak amplitude is 160 over 200 millivolts. And so the actual gain is also 0.8. And so we managed almost no discrepancy in this example. Actually, to 1 decimal place, you won't see much discrepancy, but when we display 2 or 3 decimal places, you will see a slight difference. All right, so that's our scoreboard architecture. Let's drill down briefly into some of the details, give you a better idea of how this works. So our entire SPICE-based reference model is a set of 8 tables, an unpacked array. If you're not familiar with these ticked curly braces, this is not a concatenation. This is a SystemVerilog array literal that allows you to assign an entire array in aggregate all at once. So it's an unpacked array of 8 lookup tables, each one generated from a SPICE run. Here's the select table function, which you pass in the current mode, and it uses the case statement to look up the match. And in our case, it was mode 7. So it will take this particular look table for mode 7 and assign it to our variable gold ref. So here's our scoreboard code. Some of the setup, I'll just comment briefly. The scoreboard needs both types of packets, so we declare both. It also needs to declare 2 FIFOs, and it has a build phase and connect phase to hook those up. And then during the run phase task, we're going to call this function goldVout, which scans through the lookup table stored in goldref, finds the closest match to 34, and outputs the real voltage, 80 millivolts. And so that's how we output the expected response. Let's look at the run phase task in more detail inside the scoreboard. This is a forever loop. You may be wondering, well, how does it end? We'll answer that question in a moment. Anyway, we get the latest packet, driver side from TX50, monitor side from RX50. Using the FIFOs enables us to use different timings and even different data rates if we had to for these streams of packets. Then we call select table to put the correct table into goldref. And then here we call goldVout, and we do the lookup. And so we can now compute the discrepancy between the actual transfer gain computed here and the expected transfer gain computed here. And so that's how the run phase test works. By the way, what causes the forever loop to terminate is that these get methods are blocking. So when the FIFO becomes empty, they scream to a halt and the loop terminates. Completely untimed. Okay, another detail. How did we generate these 8 lookup tables using HSPICE? Well, for each mode, we ran a linear SPICE AC analysis, generated 100-odd data points, and then we cut and pasted just the numerical data, fed it into a simple awk script, and recast it into a syntactically correct SystemVerilog associative array. So the array has real elements like 54 millivolts for each frequency index, like 119 kilohertz. And again, this is an array literal, not a concatenation. So that's how we generated the tables. Let's look at a transcript in actual run. So this is kind of merging some of the data in a longer run. This part of the transcript only shows up if we set the UVM verbosity high, and it shows all the details. 34 kilohertz, mode M7, bypass bit low, and here's the actual gain of 0.8. The rest of this is a tabular printout. We actually achieved that by using the a sub-object inside of our scoreboard we call scorecard. It's basically an array of structures that collect all these values during the run, and then at the end just print them out in this nice tabular format using one of the UVM generic reporting methods. So there is our run for 10 trials. All right, another quick review question. session. Again, a good time to feed in your Q&A. So let's see, each pair of packets represents a single, I think everybody got that, transaction. Using associative arrays for our lookup tables. In SystemVerilog, these kinds of arrays can take any data type for the index. So one big advantage is that the index can be non-contiguous. You can do a non-linear spice analysis and still use the associative array table method. Cyclic random variables, they only start repeating when you've used all the values. Any questions, Jeha?
So we're still waiting for an open question. We had one question posted earlier, but I answered it. Well, while we're waiting, there's another simple question I'd like to ask. So I noticed there is a class named UVM sequence, and there's also a class named UVM sequencer. So what's the difference between sequencer and a sequence?
Good question. So in our block diagram, the sequencer was hooked up via TLM path to the driver. And so they were both components, fixed components within the class hierarchy. So the sequencer is a fixed component within the hierarchy that's built at time 0. The sequence is a transitory object that comes into being as you start a stream of packets on the sequencer. And it's transitory, it's not a fixed part of the hierarchy. You may have a test bench where you run 100 sequences, then do something else, and then start running some other sequences, all using the same sequencer.
Okay. So the code that you described for the sequence, does that sit inside the sequencer?
No.
Oh.
No, they interact via that handshake mechanism that I mentioned. So,
oh yeah, so the one, so I understand it's a handshake between the sequencer and the driver. So the sequencer code instantiate the sequence class, no? Sequence instance, or I don't know how to call it.
You know, let me proceed because that may get answered on one of the slides about
later.
Come up.
Got it.
I will go into detail there. So let's go on to section 7 and actually see how this test suite, this series of of packets in our sequence is actually run. So before we get started, we have to take a more detailed look at this topmost module, which we call UVM TB. This is actually the top module elaborated by the VCS or Excellium or Model Sim logic simulator that you use. If you just write a bunch of class code, a simulator can't really get a handle on that. We have to elaborate a top-level module. And so this module, as we've mentioned, defines the periodic clock waveform, the reset pulse, instantiates the fixture, as well as the 2 interface buses that connect it with the class hierarchy. And it has an initial block, which is where we called set to put the diff and mif values into the centralized database. Then what kicks the simulation off, the advancement of time off, is this UVM method run test. And we give it an argument, the top-level test suite class that we want to run. Could also pass that from the command line, by the way, as a plus arg. So here's what happens. As run test is executed, the string name of the argument tells the UVM machinery, specifically the factory, go ahead and instantiate this particular test suite class object. You may actually have more than one that you can run. And this is a great feature because you can specify different test suites from the command line without recompiling your code. We'll highlight this in our next project, by the way. And so here is the test suite code. It's an extension of UVM test. One of its biggest jobs is, as the previous slide clearly showed, it has to instantiate the environment that it wants to use. It does a factory create on the environment. It also gets the knobs, trials, and inactive from the UVM command line processor. If you're interested in the details, you can look at our downloadable papers for more of the coding details. Then it builds everything. And then the test suite is ready to run its run phase command. And this is where we can answer that question, Jeha. First, we're doing a simple test suite with just our one sequence filter sequence. And so we're going to first create the sequence. This is not the sequencer. This is the transitory sequence object. We're going to call it seq1. We bring down the trials knob into the sequence so we can set the length of its for loop. And then here's the answer to that question. We start this transitory sequence on the sequencer object, that pink rounded rectangle in our class block diagram. So this highlights the difference between the sequencer and the sequence. So calling start behind the scenes kicks off the body task inside that sequence. And the sequencer does the handshake with the driver. So that's how it all plays together. Then important detail here, notice we raised objection, and then when we were done, dropped objection, at which point, if there's no other raised objections in the machinery, UVM can halt the whole simulation. One more key detail, we don't want to drop objection too soon because after we've applied that last packet, whatever frequency, whatever mode, we need to allow at least half a cycle settling time before we can measure the output amplitude. So we needed to add at least half a cycle. We gave it a whole cycle using the set drain time method. So the simulator will continue an extra cycle to allow settling time. This is perhaps the simplest way to do that. Very handy for an analog mixed signal design. Okay, here's a quick look at our test bench topology, which can be printed out using this command. And sure enough, here is our test suite class that was instantiated by the factory machinery, and it gave it the fixed instance name UVM test top. It instantiates the environment, which in turn contains two agents and also a coverage and scoreboard mode, a scoreboard block with the FIFOs inside of it. And finally, here is the XMODEL based command line. Some of this is simulator specific. We'll assume the VCS simulator. So we're going to run this XMODEL command in such a way that we only compile and elaborate the SystemVerilog source code files mentioned in our manifest file, from the lowest level DUT, which has the auto-extracted models and details, on up to the fixture, the interface, the monitor and driver, on up to the top level test bench, which is indicated here as the top level module for elaboration purposes. And then we can, when that's done, issue a separate VCS specific SymV command to actually run the simulation for this test length, 10 trials, 5 inactive, and we're doing this at UVM verbosity high. And this is supported for all these commercial logic simulators. Okay, let's try to wrap up shortly here and allow time for Q&A. So let's take our simple one sequence test suite and extend it to 3. So we've been running the filter in normal mode. Now we'll make that just sequence 1 and adjust its length using trials. But now we want a second sequence where we finally power down the DUT, put it in bypass mode, and conserve battery power for a while. And this will last for inactive clock cycles. And then that'll be sequence 2. And then we'll come out of power down. And to keep it simple, we'll just have a fixed length number of cycles 4. And we want to verify that we can resume basic filter operation after the power down phase. So easy to extend our run phase task of our test suite. We just declare these 2 other sequences and we run through the same executable code. I should have mentioned that executable code here is shown in blue. Declarative code is shown in this plum color. So for each sequence, we factory create it. We pass any knobs down, inactive, trials, or both. And then we launch the sequence on our sequencer using that start method. And so we just repeat this series of commands for each sequence. So that's a very simple way to exercise a DUT and run a complete test suite. In UVM, there are far more sophisticated things you can do. We don't get into it in this simple webinar, but you can have hierarchical sequences, which are composed of subsequences, starting from a root sequence. You can have, with a fork join block, you can run parallel, or perhaps we should say concurrent sequences. You can even have reactive sequences where the sequencer and the driver sends response data back to the sequencer, which can then change sequences in midstream. We've already seen the class code for our basic sequence filter, and resume is no different. So let's just focus on the middle sequence, the bypass sequence. This is when we're in power down mode. There's nothing here to randomize. So about all we do in this loop, which has a length of inactive, about all we do is that for, let's say inactive is 4. For 3 cycles, we stay in this power down bypass state, and then we automatically transition to this single wait cycle where we're restoring the VDD and the VBN bias voltages, and then we automatically transition onto the resume state. So really all we have to do is to deassert the bypass bit to resume normal operation. And here's the output for a typical run. So 6 trials, 4 inactive states, 4 resume. Notice these 3 sequences are run consecutively. There's no time gaps in between. And we're introducing this state variable and printing it out. It's a handy debug aid to tell where you are during the test suite. And so for those pink highlighted cycles, we're in an inactive state. And you may be thinking, if you're a verification guy, gee, wouldn't it be nice if I could get some verification done even during those power down cycles? Because we may need hundreds of those cycles for our system on chip. Well, you can using analog assertions. In our downloadable papers, we talk about two assertions, one of which checks the bias voltage. Is it restored during the wait state to its nominal 700 millivolt level? For now, though, for lack of time, we'll focus on this simpler assertion where during the bypass power down state, we want to be sure that the IDD current has fallen from the milliampere level to the nanoampere level. In other words, it's just a leakage current. So with the help of XMODEL primitives, we can easily add this iPro primitive to the current supply line going into the op-amp. So think of it as a nanoammeter. It outputs an instantaneous current value as an X-real variable. We want to avoid any transients, so let's pipe it into the measure max primitive, which over a finite interval between tick and tock outputs the max IDD as a real variable, and you can directly refer to that in SystemVerilog assertion code. And so we're measuring the max current over this yellow highlighted time interval. So we have full use of all SystemVerilog assertion syntax. As usual, for any concurrent assertion, we declare a property first. We call this leakage pro. And even though we're referring to this as an analog assertion, the checking is not done in continuous time. It's done at discrete time instance, specified in this example, rising edges of our packet clock. That's when the checks are done. Now, you don't want to bog down your simulator to initiate checks on every clock edge. So we include this trigger clause, and only when we've just entered bypass state, power down state, when this equality expression has risen to logic 1, only then do we initiate the checking and we make the test. Is the real IDD value less than 10 nanoamps? Then with that named property available, we direct the simulator to check it using this assertion, and we have a pass clause and a fail clause to report the results. Notice we're using the UVM report info method to report a pass, and we're using UVM report warning, a more severe report when it fails. So we can get some useful verification done even during power down. Guideline where to put this assertion code. You can put it in different places, but perhaps the simplest approach, just stick it in the fixture where you have easy access to currents and voltages. And you've got over 100 XMODEL primitives to make more sophisticated checks, crossing levels, threshold values. Here's the simulation run for trials equal to 6, inactive equal to 4. We're showing our state variable as a nice visual debug aid. Notice the leakage assertion did pass at the very end of the bypass cycle. But wow, the bias voltage assertion failed. That's due to a deliberately injected failure. We did it just tweaking the condition, but in general, in UVM, you could use factory substitution to do that in a more elegant way by injecting an error packet instead of the default packet or sequence by the factory without altering or recompiling the code. So there's our run. Let's finish up with the functional coverage. I hope this will still leave us a few minutes for Q&A. So let's answer the question, gee, with this wide passband of our filter and all these modes, how do we have any idea we've covered all the functionality of interest? Are there uncovered features that could hide lurking bugs? Well, here's our broadcast TLM path. When the driver calls write, it sends the latest packet on up to all subscribers, including the coverage block. And the cover group, which we'll see on the next slide, sees a frequency of 34, realizes, hey, that's within a user-defined bin between 20 and 39 kilohertz. So it drops a token into this particular bin. It also sees mode M7, drops that into the mode M7 bin. And so we're building up statistics on whether we've covered all the frequencies and modes. And all you need to do is to write a cover group in your coverage object to tell the simulator to start compiling coverage statistics. Here's a simple cover group inside of our coverage class. Because this was extended from UVM subscriber, the base class, it has this built-in export with this fixed name. So it's easy to hook up to the TLM pathway. Anyway, here's a cover group with just one cover point. We'll add a couple later. But this is any variable or expression, in this case, the integer frequency property of our data packet, TX packet. And we've arbitrarily subdivided our passband into 6 bins. I think of these as, I like hardware analogies, think of those as those yellow bins you can buy at Walmart. And so after just 20 trials, we've easily hit 100% coverage. In fact, most of the bins have been covered multiple times. One of them was only covered once, but hey, we met 100% coverage on this cover point easily. So just the presence of the cover group will tell VCS to begin tracking coverage. It'll stuff the information into a Linux subdirectory. Let's add more coverage requirements. What about the mode? Well, because we enumerated mode, no need to mess with manual bins. Enumerated variables are binned automatically based on the size of the set. We had 8 modes, there'll be 8 bins, 1 for each value. But hey, we ought to also monitor the combinations of mode and frequencies that we've covered. This is called cross coverage and uses the keyword cross. And so 8 modes times 6 frequency bins, total of 48. As it turns out, that's not as easy to hit 100% coverage. In fact, we just ran for 40 trials. Here it is Tuesday afternoon. We know we have a verification team meeting late Friday afternoon, and gee, we're only hitting 65% coverage. So what are we going to do? Well, we're going to show you how to up the coverage to 100% efficiently. But first, let's answer a common question. When during the clock cycle are these values like fint or mode actually sampled? Well, since we have seamless integration with SystemVerilog, there's various ways you could do this. You could, in the cover group, specify a clocking event and then have the sampling done automatically. We chose a finer means of control. we procedurally trigger the sampling by calling this built-in sample method only under certain conditions. After all, we want to compile coverage metrics only during the normal filter operation states filter and resume, not in bypass or wait. And so we have this handy write function. By the way, rather confusing feature of UVM, but this is not the same as the write function we saw earlier called by the driver. It just happens to have the same name. When the driver calls its write, it'll trigger all these subscriber write methods, such as the one in our coverage block, and it'll only if we're in filter or resume state, it'll call sample. By the way, another guideline based on a hard-learned lesson. In the base class, this write function is actually a pure virtual function. In other words, it has a fixed prototype that you have to honor. So don't try to change its return type or argument count or argument name. I didn't like T. I tried to give it a more description name. You wind up with an immediate error or at least a strong warning. Finally, can we hit 100%? Well, the cross coverage, there's 48 bins. You only have a 2% chance of hitting any one bin. So it takes a while. In fact, by 64, the curve, the coverage curve, there's kind of a knee, things sort of level off. And by this time, we still have 2 uncovered bins. And so you just have to keep upping the number of trials. One thing you can do to improve efficiency, though, if you're already doing regression testing, nightly testing, you can merge 2 runs with different random seeds. So these blue squares, this benchmark, we merged 2 different seeds. The VCS command, Unified Report Generator, merges the 2 databases together. And after only about 150 trials, we hit 100%. So you can hit 100% coverage and make sure you've adequately covered all of the features in your analog mixed signal block. So that's the end of our webinar. Hope you've enjoyed it. These are some summary of some takeaway points, and we've got some things you can download, including the PDF of these slides, and even the UVM test bench itself, which is about 900 lines of code, and a lot of good webinars on the Scientific Analog site. So I'll turn it over to Jeha for Q&A.
Yes, we have a few questions posted. This first question is from Paul. He says, this webinar was my first introduction to UVM. Are there any well-known resources where I can learn more?
Yes, I can highly recommend any of Cliff Cummings' articles available at his website. Many of them are DVCon papers, and his papers go into a lot of depth, but the first section or 2 often gives you a pretty good tutorial view of the subject. There is also a lot of good information available on the DULAS website. They even have a publicly available simulator that you can use on the web to try out simple examples. So it is a steep learning curve. Oh, let me also mention, I'll hold this up, my friend Srivatsa, will this show up? Well, I call it, it's the green, I call it the green guide to UVM. Here it is.
And, yeah, there.
It's entitled Practical UVM Step by Step. A lot of good information.
Okay. One notice before I give you the second question. Some people are asking for the PDH code. I guess it's some code for you to get recognition from IEEE. Unfortunately, I haven't got it before the start of the webinar, but I sent an email to them asking for it. So once I get them, I will send it out to all the attendees of this webinar through email. So please rest assured, I will send you the information. Okay, so here's the second question from Lucas. Any specific reason for monitoring the inputs on the driver and not on a specific input monitor? If you wanted to reuse the agent without sending any stimuli as a passive agent, we would miss the inputs, right?
Yeah, great question, and you're absolutely right, Ludwig. I only did it this way because you're right. If there are any drop packets, you could be feeding information to the scoreboard that was never actually launched. So you're absolutely right. But I did it that way just really to simplify this tutorial. It turns out that in our previous OOP-based test bench articles, we did do it your way using the monitor. So I was just trying to illustrate a different approach that made the diagrams a little bit more readable. But you're absolutely correct. At least UVM, gives you a lot of leeway in how you architect your test bench.
Oh, so I guess that's it. And we're a little over time. So I'd like to thank everyone for joining this webinar. And I'd like to thank Charles for giving an excellent presentation. And just one last notice that the presentation slides that Charles used today, including the source code for the UVM test benches, will be posted on our website under the link that Charles is just showing. And once we get the recording, we'll also post the recording so you can actually watch, so that you can watch it again or pass it on to your colleagues. All right, this is it. Thank you, everyone, and hope you have the nice rest of the day.